We present directed diffusion, direct control of object placement through attention guidance. Text-guided diffusion models such as DALL-E 2, Imagen, and Stable Diffusion are able to generate an effectively endless variety of images. However, these models often struggle to compose scenes containing multiple objects. For instance, the images above are missing subjects, such as house and dog. In addition, the words upper left are ignored, and requested interactions such as the bear watching the bird are missing. Visual storytelling requires control over representation and positioning of multiple objects. However, existing methods for text-guided image synthesis, including Stable Diffusion, fail to meet this need. Our work endeavors to address this problem. Recent advancements such as DDPM, DDIM, and LDM have produced significant milestones in terms of both quality and performance. Two recent works related to ours are blended latent diffusion and composable diffusion. The former focuses on methods for local editing, while the latter explores scene compositing. Our work provides control of placement and compositing in a unified framework. Our work exploits two fundamental characteristics of Stable Diffusion. First, the denoising makes rapid progress in the initial steps, where the overall position and shape of objects is established, and then transitions to gradual refinement of the details. The cross-attention maps for each prompt word reflect the corresponding object placement. Using these observations, we edit the cross-attention maps during the initial steps, as indicated by the star, to control object placement. Secondly, the clip text encoder utilizes a maximum sequence token limit of 77. When the length of the prompt is shorter than 77, we term those cross-attention maps not associated with word tokens as trailing attention maps. We show that the desired cross-activation maps for the directed prompt words can be obtained by injecting Gaussian noise into selected trailing maps. Please see the paper for details. Now we explain our core method. Here we start with the denoising U-Net and text embedding model that processes the prompt. Note that the models are fixed and will not be trained in our method. Next, in each U-Net layer at each editing time step, we calculate the cross-attention maps between the latent query and the key and value of the text conditioning. Then, we produce a cross-attention map that matches the user-guided bounding box by optimizing an objective to find the best weighted combination of the trailing attention maps. Next, we pass the reweighted trailing attention maps to the next layer. Finally, we ask the original Stable Diffusion pipeline to refine the result in the second phase. We will now present several experiments that compare directed diffusion with the original Stable Diffusion. First, we show the original Stable Diffusion results for 3 different prompts. We next demonstrate our DD result, placing the object in each of the 4 quadrants and in the center, as indicated in green. Similarly, we now run our DD algorithm with the bounding box moving in a sliding window fashion. DD is easy to extend to different kinds of tasks. First, we show scene compositing. Our core method positions the directed object effectively. However, it directs the location of only a single object. We introduce a scene compositing method to place multiple objects while successfully producing interaction effects such as shadows. Given the user-defined directed words in the prompt and the corresponding bounding boxes, we apply directed diffusion on all directed objects. Then we aggregate the individual predicted latent noise with the whole prompt condition during compositing. Here we show examples of the prompt: a red cube above the blue sphere, appended with several different locations. Note correct interactions such as the occlusion of the cube by the sphere, and the shadow of the sphere on the ground. And here are examples of the prompt: a bear watching a bird, in different contexts. Unlike Stable Diffusion, the bear is facing the bird in each of our results. After scene compositing, we also introduce placement fine-tuning to give the artist fine-grained control of the object location. After seeing the synthesized image, the artist may wish to move the directed object again. However, moving the bounding box will generally cause object identity to change somewhat. Placement fine-tuning allows for additional position changes, while generally preserving the subject identity and background. To obtain the refined position of the directed object, we first automatically generate the masks from the cross-attention map for the subject and the region of the background to be in-painted. These will be integrated as the initial latent for the denoising Stable Diffusion. Next, we ask Stable Diffusion to keep the target directed object as constant as possible. Simultaneously, the background is filled contextually with respect to the fine-tuned object. Our findings demonstrate that users can effortlessly manipulate the object placement without substantially altering the content or background. Thank you for watching.